Good evening, everybody. Welcome to the December meeting of the Guildford Astronomical Society. I'd like to particularly welcome new members. Are there any new members tonight? Welcome. And it looks as though you're well looked after. And were there some at the back there? All right. Are you being looked after? No, you will be. Don't worry. And guests. I'd like to welcome guests tonight. Are there any guests tonight? There is one. Good. Dr. Colin McGill can't be with us tonight, so I'm standing in for him. I'm Tony Quester, the observatory coordinator. After the break, actually during the break, there are going to be seasonal repasts in the form of mince pies. Is that it? Just mince pies. Okay, just mince pies. All right. After the break, Pam Noon will be doing the What's Up, and Max Dobrez and I will be giving a very short summary of GAS's potential project to become a charity. And as Max is not here, I guess it'll be me. So, right, tonight's main speaker is Dr. Paul Town. And I've spent some time putting a few notes together about Paul's extensive career in science and astronomy. Forgive me, I'm going to read it. I didn't know I was going to be doing this until recently. Paul's main background covers a number of astronomy-related areas. He started in the late 70s with solar and stellar physics, mostly theoretical modeling at Utrecht University, leading to the award of his Doctor of Astrophysics degree in 1982. He then began postdoctoral research in theoretical physics at Oxford University. From there, in 1985, he went to work at NASA Goddard Space Flight Center, first in the solar physics branch, later in the Space Science Data Center, working on identifying and describing data sets relevant for climate studies. In the late 90s, he worked on teams proposing remote sensing instruments. In the early 2000s, he worked on creating a ground processing system for the ozone monitoring instrument satellite. In 2005, he joined MSSL, where he's still working, first on the solar SOHO project, Command and Data Handling System, instrument calibration. And in 2008, he joined the Swift team, that's the Neil Gehrels Swift Observatory, to provide support for the operations of the ultraviolet and optical telescope. The Swift team was involved in the discovery of superluminous supernovae and got the ultraviolet emission of the gravitational wave event from the double neutron star merger in 2017. That was not just a sensation to astronomers, but to the whole world of science. I think Paul's own view of his interests is worth retelling. His interests and work is worth retelling. Paul is fascinated by explosive, non-linear phenomenon. In other words, not necessarily predictable. You don't know what's going to happen. Currently, his interests are transients like novae, supernovae, blazars, gamma ray bursters, electromagnetic radiation from the sources of gravitational waves. His interests are spread over a range of astronomical objects because he finds the physics of the processes of energetic events fascinating. Besides the science, Paul feels that contributing to the infrastructure of science is important in the form of advocating a discovery service for science data, managing and reorganizing the Astronomical Data Center at NASA's Goddard Center, working on the development of several Earth remoting sensor missions, and contributing to solving the climate crisis. Paul has written about 150 scientific papers on the subjects he's covered. Presently works on the calibration of the Neil Gehrels Swift Observatory's ultraviolet optical telescope. And his subject tonight covers 20 years of that observatory's achievement. So, ladies and gentlemen, please welcome Paul Kuin.
Well, thank you so much for the introduction. Actually, I didn't write all those papers. I usually get other people to write it, which makes life lots easier. So the Swift satellite was launched in 2004. So a few weeks ago, it was 20 years. And they even made the new 20 with a satellite icon kind of thing, which is always pretty to look at. Now let me see if I can make this go further. Probably. So not in a special order, but I'll start talking a bit about the details of the Swift satellite. There's 3 instruments, and we'll go over what all these instruments do, and they all look at the same time, the same direction, although some look wide and some look narrow. So, and then I'll talk about some of these special objects that we have been following or have discovered. And during that, I'll just here and there say, okay, this is something new that we are doing these days. All right. Now, so if you look to the left, there is a cartoon or picture of the satellite. So most satellites have a spacecraft bus, they call it. It's just something that has a lot of the hardware that all the satellites need in it, like reaction wheels and that kind of stuff. And then on top, there's 3 instruments. One is called UVOT, that is the Ultraviolet and Optical Telescope. At MSSL, we have still one of these big tubes. It's about 2 meters long and this wide, which was one of the ones that was used for vibration testing and for thermal testing, while they were building actually its sister instrument, optical monitor, X-ray XMM Newton satellite. So this was hardware that was lying around after the XMM instrument was built, and it was a few years later. So unlike the XMM instrument, this one has a lot more compute power in the processing. Then next to it is the X-ray telescope, and we'll look at all these a little bit more in detail. The only thing I want to say about that, it's a big box, and in it has little boxes, and the little boxes are all detectors. So if a gamma ray, which is a very high energy photon, comes through, then the certain boxes in the big box will know, oh, something came by, and they can measure the energy of it. And then there is this trick. They put something they call the coded mask in front of the detector. So the mask makes a kind of a shadow and based on the shadow, you can tell which direction it's coming from. So if you have a source somewhere in the sky, if it goes through the coded mask, you can get a position about 3 arc minutes accurate, which is very accurate for a gamma ray instrument on a spacecraft. And if it comes from another direction and it doesn't go through the coded mask, you still get a detection, but you cannot really tell where it is coming from very well. So every now and then you get one of these people that are really smart and bright and are taking on things like, say, why don't we use these photons that don't go through the coded mask? Maybe we can still determine where they're coming from. And that has been done recently after a few years of work. They have that capability now. It's not as accurate. It depends a little bit on where in the sky it's coming from. but it helps in case, you know, in case there's a gamma ray burst that's really bright, you get still a pretty good position. And what you can do then is say, oh, we don't know exactly where it is on the sky. 3 arc minutes, you can point that with the narrow field instruments like the X-ray telescope and the optical UV telescope. But if it's, you know, more uncertain, what you can do is you can take snapshots in a tiling pattern and still find the source. So that's a new development from the last 2 years. It was officially developed, the tiling capability, by because we needed it for gravitational wave follow-up. The gravitational wave detectors give you a really large area on the sky. No, if it's 10 degrees, you're happy. If it's 100 degrees, we don't follow up anymore. Now, this is a composite image. So it's looking at M31, so the Andromeda Nebula. And if you look at the top, you see this edge, and that's one of the fields taken. So this is combined exposures of the Andromeda Nebula, but you know, not the very outer regions. And it's a lot of them that were taken. This looks different from when you see it from an optical telescope, because this is actually a false color image from the ultraviolet observations that the ultraviolet optical telescope can take. So the wavelengths are something like 170 to 300 nanometers. And then you have 3 filters in that. Now you can see at the bottom, there's a very bright object with a little circle around it. That circle is due to scattered light in the telescope. So that's not real in the sky. It's just that this really bright object is also giving some scattered light, and it gets focused in sort of a ring. So that happens always when we have a really bright source. And in the center of those sources, it's often dark because of the way the detector works. Now, this is a layout of the ultraviolet and optical telescope that took all those images, and the light comes in from the left and then gets bounced off a primary mirror. The mirror is about 30 centimeters, so it's about a foot in diameter. And then it hits a secondary mirror, reflected onto a little flat mirror that directs it into a filter wheel on either side. So when the satellite was planned, it was planned to have 2 different detector assemblies, different filters, including infrared. But there was a problem with the infrared ones. So there's basically 2 copies of the same kind of filters on the left and on the right. When the satellite was launched, they tried out which one is the best. And since 2005, somewhere in February, March, one of the detectors has been used continuously. And of course, after 20 years, you don't really want to switch it to the other detector assembly, which is not calibrated, also because something might go wrong. The mission was initially planned to work at least 2 years, and it's now 20. So it's a lot. It's a lot to ask if you have a problem from yeah, let's switch, which we don't want to do. Now I'll show you a picture of the detector, because it's not a normal detector as is being used in a lot of cases, like in your video camera. Let's go. So this is the assembly with the filter wheels, without the filter wheels, I should say. So once they built this, there's an engine that turns it around, and one of the questions was, from how long will it last? And so they in the lab they let it run for a couple of months, did 1 million terms, and then said, well, we're never going to need the 1 million terms. But yeah, it has been going fine, even though it is over, double what it was rated for. So you see all these holes, there's filters in them, and one of them is a blank filter that blocks the light, and one of them is an open filter that lets all the light through. So if you that, then the light that comes through is determined by what the telescope will actually reflect and what it will absorb. So in the short wavelength and absorption is determined by the photocathode on the detector, which I will get to in a moment. And on the long wavelength, and I think it has to do something with the optics, and I can't quite remember what it was. So this is a schematic of the detector, because the thing is only, the CCD is only this big, and that's at the bottom. And then you have a fiber taper, but just another tiny thing. And then you have what's called MCPs. So there's 3 plates. Each plate has a lot of really tiny holes in it. The holes are like a hair, tiny hair thick. And above that is a photocathode. So what happens, the light falls on the photocathode, and it turns the energy of the light into an electron. Now that electron will hit the MCP, and the MCPs have a voltage over them. So once it hits one of these holes in the MCP, it will start bouncing back and forth and kick out a lot of more electrons from the metal or the glass of the MCP. And so after you do that, 1 electron turns into 1,000. You do that again, it turns into 1 million. At the end, I think there's some inefficiencies. You get about 100,000 out of each photon, but it spreads a little bit. So what happens is when all these electrons fall on the CCD, that actually is similar to things you have in your cameras, they are read out, and it is constructed in such a way that the photon splash falls over around what they call pixels, about 3 pixels on each axis, so 9 pixels in total. And that's read out. The readout will tell from each pixel how many photons or how many electrons it got. And then the electronics tries to get very quickly the best position. And although the CCD detector is only 256 by 256, and you only use a little part of it, the resolution is about 2048. So each pixel, so the accuracy is about 1/8 of a pixel in each direction, X and Y. And that is what is actually stored then on board, either in a kind of an image array where you keep adding how much is detected, or for each detection, it records the place on the detector and the time, which they call event modes, so time-tagged photon information. And you can rebuild an image from that, but also time series and so on. The latter mode is very data intensive. So Usually you do use image mode, also because a lot of the photons in the optical region don't just come from sources themselves, but from the zodiacal light or Earthshine or other background sources. So that's what we have to work with. The UVOT, when I have no problem interrupting myself. Now the X-ray telescope, that was a design from that was used for the XMM Newton X-ray telescope. So the mirror consists of concentric sheets of some kind of material, and when an X-ray photon comes in, it's so energetic, it will penetrate materials if the angle is too big. But in this case, the angle is less than the Bruder angle, so it will scatter. So it will actually be used, so actually this is used to focus the X-rays. And then the focused X-rays get to the bottom there. There is a filter there that blocks out the optical light, mostly. Only for very bright sources, there is some optical light that goes through. And then there is a normal detector underneath that reacts to X-rays just like to optical information, and also allows you to get a measure of the energy of the X-ray photons. So it's in a way a simpler instrument than the UV optical telescope. There's no filters. There's two different readout modes, depending on whether the source is bright or whether it's faint. But it has been a real workhorse in the last 2 decades, making a lot of discoveries. So I've now talked about all the 3 instruments, but once something happens in the sky, or once you want to observe something, how do you go about it? And this is sort of like a schematic of what's happening. So in the middle is the operations center where you command the satellite. You say, oh, turn to this source, and when you turn, do it across the sky in this particular way, because if you do it in another way, you might cross some very bright source or something like that that could damage instruments. Not that that happens very often, because the software has been built in such a way that if there is a really bright source, it powers down the detectors so that they don't get damaged. But it will also switch off the instruments at that point. So that will mean that you lose observing time. It usually takes a few hours to bring it back up. Then it makes an observation, it sends it down to the ground station. We have a dedicated ground station in Malindi that is in Kenya. And that's then sent to somewhere in the United States. And then it's sent to Penn State and to Goddard Space Flight Center, where they process the data from the satellite. So what the satellite does, it takes all the data and puts it in these packets. They call these data packets, and each data packet has a tag from, oh, this is instrument monitoring data, this is science data from BAT, this is science data from XRT. So that at some point on the ground, there is a computer going through and sorting it all out from this belongs there, that belongs there, and so on. That's one. That's the simple thing. Now, if there is a gamma ray burst, then the instrument, if it looks at it, the BAT instrument says, oh, this is bright new gamma ray burst. It looks in the catalog. Oh, we haven't seen this before. Let's slew slew over the sky to point the X-ray telescope and the optical telescope to look at it. And that takes about 2-3 minutes. That is faster than anything else can follow up. There's some ground-based instruments that also get this signal from the satellite after it has been sent down. That takes a few minutes too, so like 6, 7, 8 minutes before the ground-based telescopes, if they have been set up to automatically react to certain messages, like, this is a really bright new source on the sky. And if they have a program that says that they have approved to look at these, then they will follow up also. But generally speaking, the ground-based ones are done more manually, and it takes longer. So a new capability is now that perhaps you have heard they're building these huge 30-meter telescopes. They're becoming operational. View surveys of the sky in the infrared mostly, and so they're also very sensitive. They're going down to 26, 27th magnitude. They're about as sensitive as the Hubble, but we expect a lot of new sources to be discovered, and some of them will be variable, and some of them may. There's so many that we expect each night 10,000 or so, and so there are certain rules that they have made for the software, certain algorithms to pick out sources that are really exceptional. And there is now this new program in how the operations work that can listen in to messages coming from outside, from specific places, and react automatically to it by sending new commands to the spacecraft. It basically reschedules everything that was already scheduled. And the spacecraft can then observe those things. It has been tested out already, so it kind of works. Every now and then there's a bug that is discovered. And we have somebody at the XRT team, Jamie. He's amazing. I mean, he wrote all these Python scripts to do these things, and say, "Oh, there's a little problem." We go, he said, "Oh, I think I found it." And it's, I don't know if you have ever done programming, but I wouldn't be able to do it that quickly. And then anyway, the data is then made public once the data center at Goddard Space Flight Center that's near Washington, D.C. If they're processed it, they just put it online, and you can download the files. And if you know what to do with it, then you can make nice pictures and so on. The data is also downloaded to Leicester, where there is the XRT group. They built mainly the X-ray telescope, and their data center also allows you to automatically process the data. So you go online to swift.ac.uk and say, I want to have the X-ray data from particular star that you like. And if they have observed it, we only have observed about a percent of the sky, then it can process that for you, and you can download it, and you can get the light curve in the X-ray, you can get the spectrum, and so on. So there's a lot that has been done by the Swift team over the years, and people have taken advantage of it. People will study a particular source and say, hey, I can also see if there's some X-rays that Swift has observed. And okay, so let's go to some of the, it's difficult to choose. So I made a list, and then I just picked the top ones that I like. You may like other ones. So we'll start with the brightest GRB. That was 2 years ago, I think. It's one of those things. You say, there's something weird going on. So there was this GRB that was observed, but then the Fermi satellite observed it nearly an hour earlier. So, and the reason that our satellite didn't go to it is that it was a little bit outside the field of view, but it was also so bright that the software was saying, this can't be real. It didn't go look until it got a little bit fainter. But yeah, it was a really exceptional one. We just got a new person on the team who had been assigned to take care of this bus. And I say, oh, somebody help her get it all out. So the thing was with the X-ray telescope, we saw these rings once before. I don't remember when, but this one, it was so bright that Andy Beardmore from Leicester, who did these things for the last one, said, well, normally if it's really bright, they don't do imaging with the X-ray telescope because it's difficult to calibrate than what you get. The thing in the middle is just way too bright. But then they did take these images, and they several over the period of about a week or two, and you can see them change. So these rings expand a little bit. What do we see here? So it's X-rays coming from the gamma ray burst, very far outside the galaxy. It gets into the galaxy. We're sitting here, and it's going through the galaxy. And there's dust clouds here and there. And each time you see a dust cloud, the light scatters, and you see a ring appear where the light just scatters in the right way. So this you can use this in certain ways. I'll show you a little bit later. Basically, you can do an inversion and try to see what the distance is from these clouds. Right, I need to click here. So yeah, this is not Phil Evans from Leicester wrote in X. So stupidly really bright. That's typically him. So I thought I had to show you this. So, but despite it being so bright in the gamma rays and X-rays, and the UVOT, it wasn't really that bright. It was all these dust clouds sitting between us and that really bright GRB that made it really faint in the UV optical. And this is in the U band. It's about 3,500 angstroms. It's a little bit bluer and narrower than the optical U bands that you normally can buy. But you can see it's there. It wasn't really that exceptional for the optical, but you can still use these data and make a light curve. So if, as a function of time, since the trigger, and that's the trigger from the GBM instrument on the Fermi satellite, you can see it starts about 1,000 seconds after, so about nearly an hour later. And the bottom shows the flux, and you can see that for the UV filters where the dust absorbs so much more than in the visible U, B, and V filters, we didn't see anything. We can only say, well, it's fainter than something. On the top, you see the X-rays. That comes from the X-ray instrument, and you see that it goes down with what they call a power law. It's just exponential decay. You don't want to see something like that in the stock market. So yeah, this is just one of the things. And then There were, of course, radio observations and all that. So people were just saying, ah, look at this. But you can take the observation, the X-rays and the gamma rays and the optical and the ultraviolet, and you can then plot it as function of the frequency of the light. So the high frequency lights are the X-rays and the gamma rays. So the X-rays are already affected by the absorption. You know, the interstellar medium absorbs, you don't see anything from there. There was this satellite EUVE that was launched in the 90s, and people had high expectations of it, but because of it was just where this absorption sits, it could only see things nearby our own system, and yeah, it's too bad. But I think EUVE observations would be very useful for exoplanet observation, where you don't have that particular problem. And then you see the optical UV that is on the left-hand side for the lower frequencies. Then they try, of course, to say, well, can we model it in some way? And they tried power laws with certain models for how the absorption from the interstellar medium goes. Now, I talked about these rings. So Andy took these data from the rings, and you saw the circle. So if you go to the middle and you go as a function of distance and then integrate over the whole circle each time, you get how many counts there are in each. So the brighter ones are a little bit higher and the lower ones a bit lower. And you can see, you can convert that to a distance in parsecs from the Bohr side to the gamma ray burst. So that it shows you that actually we're probing the interstellar medium out to about 10 parsecs or 20 parsecs. Which is kind of neat. I mean, there's no other way you can do that. That was the bright gamma ray burst. Now, I was sick at home with the flu, and this thing came through, and I remember checking it. You know, you reduce the data quickly, and you read all the messages that come through from everybody in the world who's trying to find it. So I told so I work with Matt Page, who is my supervisor, and he had this PhD student. I told the PhD student, you need to get onto this and do it, do the reduction, because I was feeling lousy. And he did that. And after about 6 hours or so, after the gamma ray burst was actually measured by the LIGO gravitational wave detectors, 2 telescopes, so more or less at the same time, this new source in this galaxy in the optical. So I think it was in the U band or in the V band, on the G band, some kind of photometric band, because they had been tiling. They had basically been looking at the brightest galaxies in the region that the LIGO observatory had tagged as being the region where there would be maybe a source. And we knew it was a binary neutron star event because those have a chirp, so the gravitational waves don't die out as quickly as for black holes. So, we went also, right, you know, you hear from the other guys we saw something there in the optical, we pointed our telescope at it, and about 2 hours later, and got ultraviolet data for it. I think I made that picture on the top. So it's the galaxy contours, and then the place where that new source was. And they called it, no, this is a different one. This is the tidal disruption event. You get to the gravitational wave one later. I've told you the story already. Yeah, this one was you know, you're just busy doing things. And then the Swift PI, the primary investigator of Swift, said, Paul, I need somebody to take on this job to look at this object. I had not looked at the data before I looked at all the data. And I was thinking, oh, well, this is kind of interesting. And yeah, if you then, it was clearly a thing of interest to a lot of people. And you know that if you're not going, then you've lost the boat and people will not be interested in looking at it. And if you want people to discuss it and think about it, then you better come out quickly and well document it. So I got a team together, about 12 people, I think. Some doing the gamma rays, some doing the X-rays. I didn't do much myself, just writing it all up and directing people. And then there's some theorists. I went to our theorist at MSSL, Kinma Wu, who is very smart. And I said, well, I think it's a TDA, a tidal disruption event. And he said, well, yeah, it must be a tidal disruption event with a white dwarf. White dwarf? Why a white dwarf? And he comes with all these arguments from, yeah, well, it's this bright and needs to be a black hole of about, 10 to the 4, 10 to the 5 solar masses. And the time scale is about right for a white dwarf tidal disruption. So yeah, we wrote this paper, and Raphael and Margotti, who I've been working with on Supernovae, wrote another paper that it was a supernova. So this one is something NASA made. And it's basically partly real and partly made by the artists after we told them what they should do. I remember iterating a bit about this. So the white dwarf it's matter that has been pushed together so much that it's mostly helium, but in a degenerate state. So the atoms share more or less all the electrons that are around them. And yeah, if that disrupts, then that energy is released. Part of the matter from the white dwarf is about half is going to the outside, or the other half falls onto the black hole. And so you get this accretion disk because it comes in a certain way, and the matter keeps turning around. And I don't know why. Well, so you get a jet which comes out on top of the plane of where the white dwarf has been flying. And yeah, X-rays were observed later. Let me get to the next picture. For a moment. So it's the door. Yeah, this is the gamma ray. This is the gravitational wave one. So it happened near a galaxy. So once these things happen in the nucleus of the galaxy, it's really difficult for us to detect it at the moment because we don't have an automated detection algorithm that works on the top of the galaxies. So if it's away from galaxies, we can see things. But yeah, this was observed by another observatory in South America. And this is what we saw. So this is the actual image with the data in it. The one when it was still bright and the one when it is more or less gone. And you see that's 6 days later. That's more or less gone because the noise from the background is just overtaking it. And you see it was about 50 megaparsecs away. The galaxy, it was nearby. It's not very well resolved in our images. And that's what we work with. That is where we get the light curves from, and that's where we get the spectra from. Now, once we got this, the thing was from, everybody was, of course, having their own data, and you can show these data, but it's not very exciting. So we had some contacts with Lawrence Livermore, and they did modeling. They had been doing modeling. They do modeling with, things that like that go boom. So they can also do models for neutron stars that merge and then basically rip, more or less rip part of the neutrons comes off, and you get this cloud of neutrons around the neutron stars. And the amazing thing is, I didn't realize that before I started reading about it, but the density of the neutronic material that is swirling around these 2 neutron stars that have been collapsing together is so high. So I don't know if you have ever heard of neutrinos. They're generated inside the sun by nuclear reactions. They just fly through the sun, they fly through the Earth. Billions, you don't notice it. These neutron stars, this ring of neutronic matter around them, it stops them. It just stops the neutrons. And the neutrons actually cause part of the reactions that make the heavy metals. Depends a bit on the neutronic fraction, the electronic neutronic fraction. So a lot of the energy comes out later because that material is so dense, even neutrons get stopped. Photons definitely don't easily come out. And so you get these models, and there's the top view, a side view, bottom view, different compositions for how much the neutrons are mixed with normal matters or normal electrons, and so on. And you try to fit that to the data you have, basically. And of course, we didn't only fit it to the data from Swift, but we collaborated. We got data from other people too. And there were about 3 main groups having different kind of models to model these neutron star mergers. Most of them had predicted that there would be no ultraviolet emission, and we saw it. So that basically put some in the bin. So yeah, I have another one here, but I found this, so I don't know if I would believe that neutron stars have these interesting patterns on the surface, but they might have. We don't know. One of the things that you must realize that we observe just points, we observe colors, and we observe how they change. But the rest we need to compare to physics in our laboratories or in stars that we can observe or other phenomena and see if they're consistent or not. And these models, these pictures that you get, and things that sometimes appear in the news, they are kind of a visualization of what is happening in our heads when we look at these things. But we might be wrong, or it might be different in some ways. Ooh. So yeah, you know, you're sitting behind your telescope, you know what you're seeing. We know what we're seeing, but then we start imagining things. I got interested in Norway. Actually, what happened was the UVOT, the Ultraviolet Optical Telescope, where I'm calibrating, it has two filters in it that are grisms. So it disperses the light of each source that you see on the sky. And it had been, there had been a nova called RS Ophiuchus in 2010, I think. And so the people in Leicester were very excited about that because they like to watch it with the X-ray telescope, and the novae explode, and then after a few days or a week, soft X-rays appear. Before that, you may still see some hard X-rays too, but much less. But so they had this, and for the optical UV telescope, they observed the grism. So there's all these grisms, and it turned out that the calibration was only done for one point on the detector in the center, and if you go a little bit away from it, say 300 pixels, the solution for the center for the dispersion, so the mapping of the pixel to the wavelength, is not correct anymore. And so they were like, we have all this beautiful data we can't do anything about. Paul, can you calibrate this? So it took me only 2 years to get it working. It was really nasty, but I got it to work. And so yeah, since then I've been interested. Now we've started talking to people and made a friend, and yeah, it's funny because that friend is Steve Shore, and he's in Pisa, and we started talking, and it turned out that around 1986, we were both working at Goddard Space Flight Center. I was at the ground floor and he was at the first floor. Never met that way. So we also are basically monitoring T Corona Borealis, which is had two eruptions, one in 1864 and one in 1946. So about 80 years apart, and so we expected that might happen again. One of the things that we saw in the older spectra is that older observations, that in about 8 years before the eruption in 1946, the source had first brightened in V and B, or fifth magnitudes, and then it got a lot fainter, and then it exploded in a nova. So now we got this period that it got brighter, and it got fainter about a year and a half ago, and now it's picking up again. I have different colors here, so if we're looking at a system this to us, and the period is 228 days, and so you can measure it. We measure it about every 2 weeks or every week now. We measure it in mostly now the UV and the U filter. We used to do also the VMB, but you can see these have not been followed recently. So it's a program that Juan, what's his name? He's in Argentina, and then Jennifer is at MIT. They have done the proposing, because I don't want to do all the proposing. You can see that the big red dots is when the secondary, which is a red giant, is in front of the white dwarf, but you can still, the accretion disk, we don't really know how big it is exactly, but the accretion disk can still peek out in some ways. Before or after. And yeah, so there's these little dips because of the looking at the system in different ways. And so far, it doesn't look like there's anything exciting going on. So we're still, we're still hoping that it go off in a few months, but who knows? We have a whole collaboration online, very loose over who is going to observe what, and that you can talk to them if you have data. A different nova. This is a nova that is in the Large Magellan Cloud, was discovered in 1968. This one has a period of about a week. And so the secondary star is not a red giant. It's a main sequence star, which is like the sun, much smaller. But going around in a week means it is much closer to its sun than, it's a binary system of a white dwarf and a main sequence star. It's like you put something really close to the sun. So you can, for example, do this was done with the ultraviolet telescope from the IUE mission. So that was one of the first ones that was launched. Was very successful. The detector was not a CCD. In those days, they didn't trust CCDs yet. It was basically, remember the old televisions? They had this big screen where basically a beam was shot at and then it lights up. It was a similar technology. And then the spectral resolution, especially the short wavelength. So you have here around 1215. You have one of the main lines from hydrogen, but you don't see it here. So what you do see is nitrogen 5. That means nitrogen atoms that have lost 4 of their electrons, and silicon 3. And these are very important transitions, because the atom, when it has, say, 3 electrons, one of the electrons gets excited to the next energy level, and then falls back, and then it falls back, it emits. And those are the most important transitions in an atom to look at. There's lots of energy levels. You can have transitions between all these energy levels, but the one from the ground to the first level is frequently used.
Sorry, could I just ask you, in terms of the time series, those would look different over each eruption, because presumably in the nova you're starting to burn different elements?
Yeah, it seems like we see in the nova similar things happen in each eruption. So the matter, the nova works like matter falls from its companion on the white dwarf. It collects there. And at some point, so much matter collects that the pressure at the bottom of the hydrogen layer that has been accreting on top of the white dwarf, which is usually helium, starts a nuclear reaction. and that runs away in milliseconds.
So it's not that it's burned its hydrogen and it's starting on helium.
No, it's not like the inside of the star, it's on the surface. And when that happens, it explosively lifts part of the accreted material and it ejects it typically with speeds of 10,000 kilometers a second, so that's really fast. And then it depends a bit what companion it has. So if it's a giant star, like Tycho Bohr or Arazov, then those have a big wind. They already lose matter all the time. If it's a main sequence star, it's very little. The solar wind is very thin, for example. And then you get more the emission from the shell that is being ejected. So if the ejected shell hits the wind from its companion in these giant systems, it mixes with them, and then it gets more complicated. Another interesting thing is that once you get this this runaway nuclear burning, so much energy comes out in a very short time. It's a radiative wave that goes out faster than, of course, the 10,000 kilometers a second. It goes with the light speed. And that radiation can excite atoms in the region around the system, and those get ionized, and then that is only a short flash. So they get ionized and starts then decaying. And so for about a day or several days, you see these emission lines, very narrow emission lines, because they're in the material out in the cold, not close to the star system, and tell you something about what's out there, how much mass loss there was beforehand. But it's a very short phenomenon. It's called flash ionization. There's all these weird things that you can find. So I wrote a paper collecting all the data about this one, which is why I know it a bit well. And then at some point you look at all the eruptions that had been predicted, and a lot of missing ones. We got to, it's about 5.6 years between eruptions. But it has been erupting consistently every 4 years since I wrote that. So, of course, what we know about these systems, you can try to model them. This is for Arazov, which is a giant, it's one of the best studied systems, a giant with a white dwarf. There have been some other models, but this one is one of the better ones. It depends a bit on what kind of boundary conditions are used in your model and so on. And I cannot show the movie because this is just pictures. So the top ones is before you get an eruption, and you can see that there's this big disk of stuff swirling around the white dwarf, and there's a top view and a side view. I mean, so you see it's kind of plain. And on the bottom, that is after the nova eruption happens, and you see there is a shock traveling through the wind. And so this causes this asymmetry, and you can see that from above, and you can also see it from the side. Of course, when the part where the secondary is, that's where the wind the densest is, and that is where it won't propagate as fast. And you can use these models with densities and temperatures and the radiation field to get estimates of how much emission you would get from all these different structures and compare. Okay. What do we have here? This was the this is the one with the shocks. What was the other one? I don't know how to go back. And somebody has put arrows in it. But yeah. So one of these things with subsequent eruptions is that you won't always see the system from the same direction. And the last eruption a few years was different in the X-rays. But if you looked at things that depend on your viewing angle, like the flash ionization affects the whole volume around it. So if you look at low density material around the system, that was exactly the same as in other eruptions. So it helps to have a model and calculate it based on Newton's law and fluid mechanics and radiation transport and all that stuff. Right. Despite that, with novae, we still have a lot of questions. We have questions with everything, but you know, I'm interested in novae, so finding the system's inclination is, for example, difficult because to get the orbital parameters, you usually use lines in the secondary, and they're not always that easy to get. Interstellar absorption to the system is not always clear. With the Gaia satellite now, we get some measure of the distance, but the problem is that Gaia distance measures are based, basically they're calibrated for single stars or for double stars that don't do anything weird. And these novae are falling in the weird class. So there is still a certain amount of leeway there, or uncertainty on the distances. Now the whole, if you have a binary system and it evolves over time, you get one white dwarf by supernova, and then the other star may also go supernova. And then you have two white dwarfs which may combine, and if they combine, they could cause a supernova 1A. And those are being used to determine the distance of things in the universe. So they're a distance measure. So the evolutionary path of these systems is still very murky. What do I have here? Yeah, so gaining mass is one of these issues. If you talk about, you know, what do these eruptions do to the companion? It's there are some models, but it's strange enough. Not much has been done about it. What has been done is credible. It could be done much better. And then we found a classical nova, which is not recurrent on a short time scale of, you know, our living 100 years or so. That the idea was, if mass is transferred from the secondary star to the white dwarf, and you have a nova explosion, then the accretion reestablishes itself in a pretty consistent way pretty quickly, like in days. And we found a system that's clearly not happening. So there is something we don't understand there. That's one of the big questions we have. And What's this? Fast blue optical transients. Yeah, these are another weird thing that the last 2 years, people watching supernovae and hunting for tidal disruption events, which were discovered maybe 15 years ago. They found some systems that, if you look at the spectrum or the colors, there's a lot more light coming out in the blue than in most other ones. So what's happening there? Something really hot, bright, is contributing to emission in the ultraviolet. So what it is? There's a proposal. It could be supernovae that exploded, and the progenitor of the supernova had already lost its outer layer, so it's basically the core of a star, and those are hotter than normal supernova. But yeah, this is still an issue of a lot of this debate. And I have here some spectra, so it's the wavelengths is at the bottom. So this is all, so it's all observed in the optical, but then moved back, or it's observed in the near UV and moved back to the far UV. So it's corrected for the redshift. And some of them are tidal disruption events. Some are, they don't know, these blue super, these blue optical transients. So they come and go. We don't know what they are. I stole this view graph, which is kind of interesting. Was made by Natalie Webb for a presentation we did to the EU. So if you look at variability time scales, how long it takes to variable, some things are fast, like stellar flares, they go up and down. And if you see one for example, in the UVOT, we see, oh, there's a new source there. Let's take another picture. Oh, there's nothing there. That's an hour later. And then you look in the catalog. Oh, there's an M star there. They are known to be flaring. So X-ray bursts and gamma ray bursts can be very short. So yeah, it can be seconds to. And then you have things like active galactic nuclei. That's the AGN, that's in the core of a galaxy. It's a supermassive black hole. And something falls in there. It takes a while to brighten and to get fainter. So yeah, there's all these kind of things that we can spend our time on. Now, so the new things that we have is that we changed all the planning software and so on, that we can respond to gravitational waves, and these new telescopes are coming online, like the LSST, and that people automatically can request observing of a new target. The program has been approved before. And some people think Swift, that's an acronym, but it isn't, called after the bird. And that's my talk. If there are questions, I'll take them.
Try again. Any questions? I have one question. Just go on.
On one of the early slides, you showed the telescope with the pattern.
Yeah.
grill across it so you could see which angle the bursts were coming from.
Yes.
So my question was, and you also mentioned that you can swing onto target much faster than other telescopes, so like than the Hubble. So do you use that pattern grill to orientate the telescope so that the rays are coming directly down the center of the scope?
Yeah, but that's not the real reason to
And it's,
go there.
it obscures a small part of the CCD, so it's not a big thing, it's just a small thing.
Yeah, so the BATS, the Burst Alert Telescope, has this coated aperture. It observes gamma rays. It doesn't use a CCD.
Yeah.
It uses little elements that react to a gamma ray.
Yeah.
Like germanium things. I don't know all the details about that. But so it can determine that the gamma ray source is, say, the sky at this position more or less.
Yeah.
And then the X-ray and optical instruments are pointed somewhere else at that time. And so it can automatically calculate how to move from one to the other in a few minutes. So yeah, that would affect the coated aperture, how it falls on the detector. And that is corrected for a while it is slowing.
Yeah.
So there is actually a database of what they call flu measurements. Even it of course detects things all the time.
Yeah.
But even when the X-ray and optical instruments were not able to observe because of the gyro problems or things like that, the gamma ray telescope keeps observing. Yeah.
Could I also ask you to explain the function of the grism? My understanding is it's like a diffraction pattern.
Yeah, it's like a prism with some extra lenses. I don't know if I can show that. I don't have it in my presentation. Let's go away from this.
So does it move the light onto different parts of the detector if you say it's a prism?
So it disperses the light. So in fact, one of the reasons I could calibrate it is you take first an image in a normal filter, you get all these stars, and then you take an image through the grism and it disperses the light, and you need to match them up to the image where you have just the stars, and you can use that as an anchor point so that you can do the wavelength solution, which matches pixels to the wavelength.
Which comes first? Is it the grill or the prism?
Let me
Does
see.
the light hit the grill first and then the prism?
Yeah. So it looks like this. So you see the little dots, and you see the long ones. Now the little dots belong to a long one. After each long one, there's a little one. The little one are the 0th order, which is still dispersed a little bit. And the long one is the 1st order. And then on the other end, you sometimes have the -1 order. The way the optics were optimized, didn't put all the power into one order. You can do that to some degree, but it's so yeah, you have here an image, and you can see these big streaks. Those are the spectrum, You can actually see that spectrum on the top has a little dip with a little ring around it, and that is probably a very bright peak, and it gets saturated around it, so that looks dark. One of the problems with the optical monitor on XMM Newton was that you get all these background sources, and the PI for this instrument decided to rotate the grism in the filter wheel so that you could just rotate the whole filter wheel and block part of the background. And this is why on the left you don't see any of these zeroth order, but you can still see the first order. And the background is there also much lower, so you get a better signal to noise. It was a brilliant idea from Keith Mason. Yeah, this shows you a bit of the optical design. So you see there's this prism and then some other optical elements that disperse the light in different colors.
Are they all lenses? So
Yeah,
where would the grill be in all of that?
I didn't design it. The guy who designed it was already gone by the time I came there. But that is my understanding. These were actual lenses.
Yeah.
And for some reason during the launch, one of them must have moved a little bit. So in the UV grism, normally if it's all done correctly, all the different orders overlap, which can be a problem. But if you look at the top one here, if you look at the right-hand side of the top dark line, you see that kind of split. And the split off is the second and the third order that normally would overlap. So you have a clean ultraviolet part of the spectrum from about 1700 to 2800 angstroms. And then it's depending on whether the source is very blue or if it's red, you get a second order that starts around 2100, but it can be offset on the top of the detector. On the bottom of the detector, it goes a little bit the other way, and the center of the detector, they overlap. So we have been using this fault to our advantage to actually get better wavelength coverage. Yeah, that's one of the funny things that I discovered.
Are there any more? Anybody have any question? I have a very simple question. Was there what's the visual magnitude of the UVOT GRB?
The BOA GRB.
Or was there a visual magnitude?
Yeah, there was a visual magnitude. I think we I don't remember. You can look at the light curve. If we can find this. What happened to this? Okay, if I do this, go to that here and make it big. Right. So the bottom one had different magnitudes. Oh, and it didn't flop. So the V one is the yellow one, and so it's about it's about 3 times 10 to minus 15. I think that is around 20th magnitude.
20.
Yeah.
So the brightest ever GRB is magnitude 20.
Yeah, yeah, that's because of all the absorption through the galaxy. It's amazing it came through.
Yeah.
Yeah.
Anybody else got any more questions?
So the brightest the instrument, the UVOT instrument can observe is 9th magnitude. Goes brighter than the optical system starts saturating, that it can't refresh fast enough.
Right.
So
Okay. Once again, thank you very much for
okay.